I'm Sam Hopkins. I'm a Miller Fellow at UC Berkeley. I work at the intersection of computer science, math, and statistics. I'm a theorist, but for me, everything starts with data. In particular, with the kind of massive data sets that we've become able to collect and harness in the last 30 or so years. And data sets like these have led to things we now take for granted, like search engines, more recent innovations like digital assistants and driverless cars, and also have had impact across the sciences, like with databases of gene sequences or astronomical images. To give you a sense of the kind of magnitude of data that we're talking about, this telescope, the LSST, when it's completed in 2022 in the Chilean desert, will collect every night enough images of the night sky to fill 120 MacBooks. So when data sets become this big, with many data points, but also lots of noise and many dimensions to the data, often the bottleneck to drawing useful conclusions from your data becomes the amount of computational resources you can throw at it. To give you a sense of what I mean, here's an example. Imagine that your data form a network, like this. Maybe it's a network of proteins, and the lines between proteins denote shared biological pathways. Or maybe it's a network of people, individuals, and the lines denote friendships on a social network. Now, networks like this in the real world, they look randomish, but underneath the randomness there's often useful structure which we would like to understand. So the question is, if you're given a network data set like this, how could you find underlying structure? One kind of structure you might be interested in is a community, or a group of individuals that is better connected to one another than they are to the rest of the network. Now, given such a data set, how would you go about finding a community? Of course, you could start guessing and checking. So here's a guess. But this guess isn't so good because it's much better connected to the rest of the network than it is to itself, kind of the opposite of a community. Or maybe you make this guess, but it has pretty much the same problem. So rapidly, this algorithmic strategy, guessing and checking, becomes computationally intractable. The issue is that there are so many possibilities to guess that you may never find a good one. In fact, in a network with n individuals, n nodes, there are something like 2 to the n potential communities to check. 2 to the n undergoes exponential growth. So very rapidly, even for small data sets, 2 to the n is much bigger than, say, the number of atoms in the known universe. And no matter how much computational power you try to harness, you will simply never be able to check all the possibilities. It turns out, though, that for this problem, there are algorithms, including some studied in my work, which are much cleverer. And they can recover communities like this, given a data set, which if I rearrange, you can see, is much better connected within itself than to the rest of the network. So this phenomenon, that naive data analysis strategies require an unreasonable and impossible amount of computation, occurs across applications, like in networks, but also in imaging or in image recognition. And it occurs in fundamental data problems, fundamental statistics problems like separating inhomogeneous data sets or doing statistics in the presence of outliers, like these points. My research focuses on two fundamental questions. Which high-dimensional, high-noise statistics problems are solvable with a reasonable amount of computation? And what makes those problems different from the ones which inherently require an unreasonable amount of computation? For more information about me and my research, you can visit the Miller website at miller.berkeley.edu.